Good morning, students. So today in this video, we're going to cover chapter 1, and that's basically talking about what organic chemistry is, and then I'm going to do a review on bonding and talk a little bit about covalent and ionic bonds. Okay, so here's our outline. Chapter 1 will be in 3 parts, and we're covering this top part today. What is organic chemistry? So let me just start in the mid-1700s. We basically have a shift. We go from something called alchemy. Alchemy basically is the notion of matter being transformed. For example, say taking a cheap metal and converting it into gold. So kind of some magical aspects to it, or finding an elixir for life. In the mid-1700s, we start transforming and evolving into modern science. We start identifying organic versus inorganic substances, organic from plants and animals, inorganic from minerals. It's not clear why they're different at this time, and individuals attributed that to some sort of vital force. So just before the 1800s, Lavoisier noticed that most organic compounds contain carbon and hydrogen, which is true. We'll see that when we identify modern organic chemistry. As we move into the 1800s, this sort of vitalistic theory, kind of the responsible force being the vital force, that's weakening because there's more scientific observation. There's the observation that organic matter, such as fat, can turn into soap and other organics, fatty acids, which might be familiar to you as making up triglycerides. The other thing is inorganic compounds, such as ammonium cyanate, can be turned into organic matter, such as urea. Modern organic chemistry is the study of carbon compounds. So that's the main thing. The compound must contain carbon. This is really shocking, but greater than 95% of known compounds contain carbon. It's ubiquitous, it's everywhere from all sorts of different types of materials such as clothes, plastics, something so different as fossil fuels, coal here, foods, drugs. So here's a triglyceride, here's morphine, here's caffeine, even in DNA. So there's so much diversity. Just to let you know, these are bond line drawings that have each point or vertex as a carbon, and you assume, so each of these lines is a bond, and then you assume that each carbon has enough hydrogens to fulfill the octet. You guys will be able to draw structures like these quite quickly. So much diversity because of this covalent bonding nature of carbon. Let's review the atom. You've got a dense nucleus, protons and neutrons. This is positively charged because of the protons. Most of the space in the atom is due to the electrons. These are negatively charged. This is important because what we talk about in this course are reactions where it's these outer valence electrons that are going to be involved in the reactivity. A solution of Schrodinger's wave equation gives us orbitals, which is critical for you guys for understanding whether or not a reaction is going to occur, how it's going to occur, what the preference is, what direction based on the geometry. So for our class, the most important ones are the s and p orbitals. And again, these sort of orbitals that came out of Schrodinger's equation, it's basically defining a region of space where the electrons are. So we can't say an electron is exactly in a certain spot, but it could be in this region, in the shaded region. And this, in a p orbital, there's a node here. It cannot be in the region here between these two lobes. The other thing is a p orbital. Just remember there are 3 different directions in the x, y, and z direction. You don't need to fill up orbitals in this course, but I put this here in case you did want to review. Basically, just know that atoms are composed of electrons that reside in these orbitals, filling up the lowest energy orbitals first. the ones that penetrate closer to the nucleus generally are the lower energy ones. You won't have to predict that. Here are just some rules if you want to review that. But let's look at oxygen. Atomic number 8, meaning it also has 8 electrons. So you feel the 1s, the 2s, the 2p, and you can see that you have your 8 electrons, but the outermost electrons in the highest shell here, in the n equals 2 shell, 2s, 2p, has 6 electrons. These are the outer valence electrons. You guys might be familiar with looking at the periodic table. It's in group 6, 6 valence electrons. You have to be able to know that for atoms, just because you will either have to draw them or just know the electrons available for bonding. Okay, look at this. There are 6 in the outer shell. What do you remember about oxygen? How it binds? Basically, oxygen generally likes to have 2 bonds and 2 lone pairs. These 2 available unpaired electrons can easily form 2 bonds, and these 2 filled guys can represent lone pairs. So later we talk a little more about hybrid orbital theory, but basically the idea is the outer 6 are available for bonding. Okay, ionic bonding. An electron's transferred, you get ions, cation and anion. This comes from the loss of an electron from the outer shell. Here my example is sodium, and it's giving its electron to chlorine to fulfill its octet. So the ionic bond is not shown, it's not visible. There isn't a sharing of electrons like there is with covalent bonding, but there's a bond here because the opposite charges attract, and that's a really strong bond. This will be relevant in our acid-base section, where we look at, for example, anions that have an actual negative charge, and they can pull off an H, essentially an acid delivering an H+. And in that case, that's really interesting because you can actually form a covalent bond. Covalent bond is electrons shared between atoms. This is the glue holding atoms together. So these are atoms not interacting, but they get close enough. The electron of one is attracted to the proton of the other. That's the reason why bonds can occur and why matter exists the way that it does. So you have this optimal distance and the electrons are shared here. So what's interesting is you have this shared bond and you could break that. In some cases, you might have one electron go to each guy. That would be a radical reaction. Or you can have, say, for example, someone picking off an H and leaving 2 electrons with another guy. That would be a polar type of reaction where you're involving plus and minus charges. Okay, so why carbon? Why is this such a big deal, making up organic chemistry? The reason is that it prefers to bond covalently. It has such a huge ionization energy. You have 4 outer electrons for carbon, so you would have to remove the 4, which takes a huge amount of energy. Compare that with sodium removing its single outer electron, only 100. So quite a bit less. So carbon prefers covalent bonding. It has 4 available unpaired electrons. It can, for example, pair with 4 H atoms with a single electron to give methane in this example. The 2 electrons is a single bond shown as a single line. Okay, what you guys want to be familiar with is electron dot and bonding, because this needs to come second nature to you. So if you don't recall this, definitely practice this. Group 1 has 1 outer valence electron, so it'll form 1 bond. It wants to have a duet, meaning 2 electrons, so sharing another electron to have it experience 2 electrons. Group 4, 4 outer electrons, same as silicon and carbon here. It prefers to 4 bonds, it could be 2 double bonds. It could be a triple bond or a single bond, but it prefers to form 4 bonds. Group 5, 5 outer electrons, so one of those will generally be a lone pair and 3 bonds. Again, it could be 3 single bonds, maybe a triple bond, etc. So all of these guys here want to form a complete octet. They want to share enough electrons to have 8 around it, except for hydrogen that actually wants only 2. So hydrogen will always be at the end. Don't ever put 2 bonds to hydrogen. Group 3, I didn't put it here, but that's boron, aluminum, etc. That is okay with 6 electrons. So it can form 3 bonds or 8 electrons, forming 4 bonds. Really pay attention and just understand there are 2 different types of electron pairs. There is the shared pair between atoms, that's a bond, a covalent bond. Then there's a non-bonding, or what we call a lone pair. We will be working with both types throughout the whole course. This can actually act as a base. Water can act as a base because it has electron density, so it has some negative, partial negative charge associated with that. And it can pick off a H off an acid. This water molecule could also act as an acid. A base can come and pick up off an H and break this bond here and release these 2 electrons back onto the O, creating hydroxide, OH minus. So there's a lot of different behavior and reactivity depending on whether you're working with covalent bonds, the electrons here, or with the lone pair. The other bonding that you'll need to know is multiple bonding. So when you build your Lewis dot structures, you need to fulfill octets and use all the valence electrons. If you had 2 carbons, put them to bond together. First start out with a single bond, and then put the hydrogens around or other atoms. If you have extra electrons and octets aren't fulfilled, put them on the central atom and try to complete octets for everything. So for acetylene here, you would do the same. You would arrive at this triply bonded structure. The one thing I want you to notice is a double bond has 2 pairs of electrons, 4 electrons, more electron density than a single bond. This one has 6 electrons in here, more electron density. That's negatively charged electrons in here. So what I want to tell you is that these guys are quite reactive. These are pi bonds. 2 of these are pi bonds, and this is a single bond, a sigma bond. And here we have a sigma bond and a pi. What I want to emphasize now is you can break pi bonds, this double bond, the second of the double bond, or one of these guys, and those can react. So we have a whole chapter on reactions with alkenes and alkynes, what we call carbon or organic compounds with double or triple bonds. Okay, so my last slide here is talking about just the typical bonding of neutral atoms. Hydrogen, you know, a single bond. These are the 4 types of bonds you can have with carbon. Group 5 can bond in this manner. Group 6, like oxygen, sulfur, selenium, 2 bonds and 2 lone pairs. Halogen's a single bond. So be familiar with this. Any deviation from this, and you're going to get a formal charge, meaning there's going to be a positive or negative formal charge to these guys. It's not normal bonding, and these are reactive species. So you guys will be drawing structures like these. Just seeing that formal charge will indicate to you reactivity of a certain part of a molecule, and also what atom is going to react. So a common one is carbon, sometimes with only 3 bonds, and an unfilled octet. And so you would actually have 3 bonds and a positive formal charge, and that's a very reactive species. We call that a carbocation. Okay, I'm going to end here and I will check in with you guys later.